In this video, I will talk about regression inference in R. Before you watch this video, please make sure that you have watched my other video called Regression Inference. I have opened up here the R script. I have downloaded the data set, put it into a directory, and basically highlight it and run the program. And I put the console instead of on the bottom to the side so you can see it a little bit better. Today, what we're going to talk about is different tests for normality of a dependent variable in the regression model, so the Shapiro-Wilk test. And then we're going to talk about t-tests for coefficient significance, the various f-tests, either for a single coefficient significance, joint coefficient significance, or overall significance. And we will conclude with the Lagrange multiplier chi-square test for coefficient significance. So this is some setup for the program, including installing the packages that would be used. And let's then read in the data set. It's called wage1.csv. We're going to use read.csv, and we're going to assign it to a wage1 data frame. Then let's select several variables: wage, education, experience, tenure, and female. And from this data set, and then let's see the first 10 observations, check the structure of the data, and then use the Stargazer to summarize the data. So these are the variables that we have, wage, and these are the first few observations, the first few rows of the data. We have education in years, experience in year, tenure as the tenure of the person in the company in years, and here is a indicator variable 0, 1, indicating if the person is female, it gets a 1. Otherwise, for males, it gets a 0. Here's the structure of the data. We have 526 observations, 5 variables that we kept. And again, these are the first few observations. And summarizing, these are the mean, standard deviation, and the min-max for the data. Note again that female is an indicator variable. Therefore, we have zeros and ones in the data. Whereas wage is a continuous variable. So let's explore this wage a little bit more. I mean, we can see that this is the mean and the standard deviation, but I would like to know a little bit more about the distribution. So to do that, we are going to be drawing a histogram of a variable. And how we're going to do this is with the ggplot. We're going to be using the data set wage1. And here we would be using the geom histogram, and the x on the x-axis we're going to be plotting wage, and then this is the color that we're going to be using. The difference with this line is that on the x-axis we want to plot the log wage. So this geom histogram is basically doing the number of counts that are for each value of the wage variable, and here for each value of the log wage variable. So if we execute this code, this is the histogram that we're going to get. And so basically this is the distribution of the wage variable. So here we have wage, all of the values for the wage, and here we have count, how many of the observations have the values that we see here. So basically what we see here is that this distribution does not look normal. So it's not the nice symmetric bell-shaped curve. We see here a distribution that is skewed to the left. And if we look in the log wage variable instead, this is the distribution that we are going to see here. Now, this one is more skewed to the right, so we see more of the observations are here on the higher end. But again, we do not see a nice symmetrical bell-shaped curve here to call this a normal distribution. So this was the visual inspection of the variables. In order to do a formal test for normality, we can actually use the Shapiro-Wilk test for normality, and we would be calling it by using Shapiro.test, and then here we are calling the wage one data set and dollar sign. Here we have the wage variable, and here we have the log wage variable. So if we execute and run this code. This is the Shapiro-Wilk test. These are the test statistic for the Shapiro-Wilk, and we're looking at the p-value. So every time we have p-value less than 0.05, we have significant results. And in this case, the null hypothesis is that we see uh, normal distribution, and the alternative is that the distribution is not normal. So therefore, we conclude that we do not have a normal distribution. Next, let's talk about a t-test for coefficient significance. So here we would like to know if a coefficient is significantly different from 0 or not. We would be running the following model here. So we're going to have a linear model. Wage would be the dependent variable. Education, experience, tenure, and female would be the independent variable. Wage one is the data frame, and the results would be stored as a model. And let's look at the summary results here that we have. So here we have the estimated coefficients, standard errors. This is the t-value, and this is the p-value for each coefficient that we have here. Uh, Again, the way we interpret these coefficients, say for example this one, is that for each additional 1 year of experience, we have $0.02 increase in wages. So now, the easiest way to do a t-test for coefficient significance is to look at the regression output here. So what we're going to be looking at here is the t-value. So here we have the coefficient divided by the standard error is the t-value. And that's true for all of the variable. The coefficient divided by the standard error is the t-value. And this p-value here shows whether or not the coefficient is significant. So if p-value is less than 0.05, we would have significant results denoted by star. And if the p-value is not less than 0.05, we would not have significant results. So we would not be having stars, and the coefficient will not be significant. So this is the easiest way to actually do a t-test, is just by looking at the p-value, or even easier to look at the stars. These stars here denote significance. So now what we quickly saw here in the table, and this is the significance of the coefficient on experience by just looking at the p-value, or whether or not this coefficient has a star. And if the p-value is less than 0.05, if there's a star, we would call this coefficient significance. Let's do things the slow way using 3 methods of testing for coefficient significance. The first hypothesis testing method would be to compare the t-statistic with the t-critical values. In order to do that, let's first go ahead and display the coefficient. And we would be doing this by using coefficients. This is the model that we estimated from before. That's the summary. And then we're going to be picking up the coefficient from this model above on experience. So basically, we're going to be picking up this coefficient here. And we're going to assign this as a variable called coefficient. To display the standard error, this is a little bit more complex here. So the standard error here would be the variance covariance matrix of this model above. We are going to be extracting diagonals and then calculating square roots. And then here, this would be the uh, for the coefficient on experience. So this long code here would give us the standard error. So if you notice the coefficient that we have here, if we encompass this line of command in parentheses, basically that it um, shows the results in the console. This one is exactly the same as this one above. And here, if we want to display the standard error, that's the standard error for the coefficient on experience. And this is the same as the standard error that we see in the regression output. So then to calculate the test statistic, the t-statistic in a t-test would be the coefficient divided by the standard error. So the coefficient divided by the standard error, we would call this t-stat. And so let's look at it, and this is 2.19. So this is the same value as this coefficient divided by this standard error. That would be the t-value that we have here. So next, let's calculate the degrees of freedom. So the degrees of freedom that we have here are going to be n minus k minus 1. N is the number of observations. K is the number of independent variables minus 1. And that is the same as the degrees of freedom for the residual. So here we would call it model. And here df.residual gives you the element of degrees of freedom for the residual in this model that we had above, right? So our model is this model here. So the degrees of freedom for the residuals, we are going to be denoting it like that. This would be 521. And so that is exactly the same as the number of observations, 526. Then from these number of observations up here, we had 4 independent variables and minus 1, and that's how we got to the 521 degrees of freedom. So now, how would we calculate the t critical value at the 5% significance level? So here we would be using QT. P is actually the p-value that we're going to be using here, 0.975. So this is the remaining of 0.025. Here we would be calling those degrees of freedom that we calculated above here. So n minus k minus 1, and lower tails equals true. So basically we would be looking at the lower tail. So this would give us a t critical value of 1.96. So many of you would remember this number 1.96 because that's the t critical value for a standard normal distribution at 5% level. So now, in order for us to figure out whether the coefficient is significant or not, we're going to be comparing this test statistic here to the t critical value. And so here we see that 2.19 is outside of the t critical value of 1.96. So therefore, we would be rejecting the null, and we would be finding that the coefficient is significant. So next, the second model here, the second method that we will be using is to compare the p-value with the significance level. So before we compare the t-statistic with the t-critical value, now we're going to be comparing the p-value with the significance level, which is typically 5%, but it could be a different significance level like 10%. So what we're going to have here is the null hypothesis would be the beta for the coefficient of experience equals 0. Here, the alternative is that beta for this coefficient does not equal 0. Okay, so the p-value is a two-tail test for a coefficient significance, and the way to find the p-value is we're going to be multiplying 2 times pt and you can see the arguments that are needed for here this function. And here we're going to be looking at the absolute value of the test statistic. These are the degrees of freedom for the residuals, and here lower test equals false. And we are going to be multiplying by 2 because we have a two-sided test here. And this would basically be the p-value for this test. So here's the p-value for this test. And if you notice, this is the same p-value as is reported in the table for the coefficient on experience above. And so if we basically scroll back up, this is the same as this p-value for the coefficient. I'm sorry, this p-value here for the coefficient on experience. Okay, so this was the p-value for the coefficient on experience, and because it's less than 0.05, we would be rejecting the null hypothesis and concluding that the coefficient is significant. We can also do a upper one-tailed test, and here the alternative is that this coefficient would be positive. Here is that it's going to be negative. And so how to calculate the p-value for an upper one-tailed test for a positive coefficient is we're going to be looking at the t-statistic, the same degrees of freedom, but lower tail equals false because for an upper tail test, we need to go from the t-statistic toward the rejection tail, which is an upper tail. And here for the lower one-tailed test, which is testing whether this coefficient is significantly negative, we would be using lower tail true because we would be going from the test statistic to the rejection tail, which is to lower tail. And so that's why we're going to be using here true. And we would be finding the p-value in the t-distribution here to for this. So basically, looking at the p-value, testing whether the coefficient is positive, this is the p-value here of 0.01. It's less than 0.05. Therefore, we conclude that the coefficient is positive. And here we are testing if the coefficient is negative, and basically the p-value is very high. So we are cannot reject the null, and therefore we the coefficient is basically non-negative. And if you look back at the coefficient is a positive number, so of course it will not test to be significantly negative here. Okay, so this was the second approach, comparing now the p-value with the significance level. So let's look at the third method for testing for coefficient significance, and this is to calculate confidence intervals here. So in order for us to calculate the confidence intervals, we would have to use the critical value at the 5% significance level. So we calculated this before with Q for um, QT. Here, P would be equal to 0.975. So the complement to this is basically 0.025 that we're leaving here in the tail and in each of the tails, and this is the degrees of freedom for the residual. And what we're getting here again is the 1.96 as the critical value. So the lower bound at the 95% confidence interval is the coefficient minus this t critical value times the standard error, and the upper bound of the same is the coefficient plus 1.96 times the standard error. So this one is with the minus, this one is with the plus. So we have 1.96 times the standard error on each side of the coefficient. This is the 95% confidence level. And so here is this confidence interval. It goes from 0.0027 goes to 0.04. So now the criteria is if the confidence interval does not contain 0, then reject the null and the coefficient is significant. So basically, our confidence interval from here to here does not contain 0, and therefore our coefficient is significantly different from 0. Okay, so now we can do the same thing for testing the coefficient to be significant at the 10% level. So what we need to do here is just for the critical value, instead of leaving 0.025 in the tail, we need to leave 0.5 in each tail so that it's a 10% significance level by leaving 5% in each tail. And we are repeating and here this critical value is 1.65. So now we're using coefficient minus this new critical value times the standard error to the coefficient plus this new critical value times the standard error. So if we want to test at the 10% level, we would be multiplying by 1.96. If we want to test at the 5% level, and get 95% confidence, we would be multiplying the standard error by 1.96. So here we have, this is the lower bound and this is the upper bound of this coefficient. And one thing you're also finding here is that the 90 percent confidence interval is basically going to be uh, uh, a little bit smaller here just because this number here is smaller by which we're multiplying the standard error. Okay, so the bottom line here is the three methods of comparing either the test statistic or the t-statistic, because we're using the t-distribution with the critical value, the p-value with the significance level, or the confidence intervals, and you're comparing that to 0, leads to the same conclusion. So as we were looking on this very same coefficient on experience, in this case, we concluded that the coefficient is significantly different from 0 with all three different methods. So again, that was the slow way of testing for coefficient significance. So this was a t-test to test for significance of a single coefficient. Now we're going to be moving to f-test. And f-test could be used also for a single coefficient significance. That's an alternative to a t-test. Most people don't do it because it's much more convenient to look at the table and do a t-test for a significance of a individual coefficient. But we can do it with the f-test, so let's start that way. Here we would be testing the null hypothesis would be that the beta for experience would be equal to 0. So if we're looking at the restricted model, if we are restricting that coefficient on experience to be equal to 0, this would be the model here. And as you notice, now we have education, tenure, and female as independent variables, but we don't have experience. Now, this is the unrestricted model. And if you see here, this experience variable is included here because it's unrestricted model. But if we restrict that this beta 2 coefficient to be equal to 0, then that's why we're not including this variable here, this term in the restricted model. So let's go ahead and estimate this linear model of wage, regress on education, tenure, and female. Notice that this does not include experience here. And these are the results. These are the coefficients. And so notice again, so this would be the restricted model. So we're summarizing the restricted model. And what we need to get from this restricted model is calculate this the sum of squares residuals for the restricted model. And the way to do that is we're going to pick up the residuals from this model above that we have here. We are going to be squaring them right here. So squaring these residuals and then summing them up. So this will be the sum of square residuals for this restricted model. So in order for us to test for coefficient significance, we would also estimate the unrestricted model. And so the unrestricted model is basically the original model that we run. So let's assign it now as the model underscore UR for unrestricted, and let's summarize this model as well. So here is the restricted model and the unrestricted model. So notice again here experience is not in the list, and here it is in the list of variables in the unrestricted uh, model. So from here, let's pick up the sum of square residuals for the unrestricted model, and we would call this SSR for unrestricted, and Q would be the number of restrictions, and the degrees of freedom for the denominator would be n minus k minus 1. N is the number of independent variables, k is the number of regressors, and minus 1. Okay, so here is the sum of square residuals for the unrestricted model. We are again picking up from this model unrestricted, which was our original model. We're picking up the residuals, squaring them right here, and summing them up. And then the degrees of freedom for the unrestricted model is just the degrees of freedom for the residuals. That's how we're going to get n minus k minus 1. And here Q would be equal to 1 because we're testing one restriction, so one coefficient being significantly different from 1. So here is the sum of squared for the unrestricted model. This is the degrees of freedom for the unrestricted model. And now what we need to do is calculate the F statistic using the sum of square for the restricted and the unrestricted model. And this is the formula, the sum of square for the restricted model minus the sum of square for the unrestricted model divided by Q, the number of restrictions, which is 1 here in this case, and then divided by the sum square for the unrestricted model divided by n minus k minus 1. So I'm calling all of these that I calculated from above, and I'm calling this the F statistic here. So displaying this F statistic is right here is 4.81. So let's calculate the F critical value. So to calculate the F critical value, we are going to be using QF. F is for the F distribution. T was for the T distribution before. We're giving it here the P, which would be 0.95. So basically, we're testing at the 5% significance level. Here we have the degrees of freedom in the numerator would be 1 because we have 1 restrictions. For the denominator would be the degrees of freedom for the unrestricted model, n minus k minus 1. And that gives us the F critical value. So because it's an upper one-tailed test here for the F test. If the F statistic is greater than the critical value, then we would reject the null and the coefficient would be significant. So here our F statistic is definitely greater than the critical value. Therefore, we are concluding that we have a significant coefficient. We can also calculate the p-value for the F test, and the way to do that is we're using p for the F test. Here we need to give it the F statistic. This F statistic we just calculated above. Degrees of freedom for the numerator, we have 1 degree of freedom because we have 1 restriction. That's our Q. And that's basically the same as this denominator here. And then the degrees of freedom for the unrestricted model, that's basically the degrees of freedom in the denominator. And here lower tail test is false because we have an upper tail test. And this is the p-value for the F-test, which is less than 0.05, and therefore we are concluding again that the coefficient is significant. Now, that was doing things a slow way. A fast way, how we're going to be doing it from now on, is if we use the R command, which is linear hypothesis. You give it the model, and then comma, experience equals 0. And so this one would basically test the coefficient on experience equals 0. So model 1 is the restricted model. Model 2, this is the full model, the unrestricted model. And the restricted model is if we put this coefficient on experience equal to 0. And what we're going to see here is this p-value here. And we also see that the F value is the same, the F statistic here is the same as we calculated above, and this is the same as the p-value. And here are those here are the basically the different sum of squares that are being used as well. And um, so notice that even though here we're saying experience equals 0, we don't test that experience itself is equal to 0. We tested the coefficient on experience, whether or not that is significantly different from 0. So, um, so that's an important distinction to make. So if we actually want to to test whether the experience itself is significantly different from 0. And by the way, this is not what we want to test here, but we're going to be using as t.test. Here from a wage 1 data set, we would be calling the variable experience mu equals 0. So we're testing it to equal to 0. And here we have that the mean of x, which is the mean of the number of years of experience, is 17 years. And so this p-value is very, very small, of course. And so we're concluding that experience itself, the variable, is significantly different from 0. Why? Because it's equal to 17. Of course, people would have positive number of years of experience in the sample, and that's not going to be equal to 0. So again, be careful that here, even though we're saying that experience is equal to 0, and here saying experience is equal to 0, we're not testing whether this experience is equal to 0. We're testing that the coefficient on experience is equal to 0. And we're concluding that it's not equal to 0. So another important point to make here is that the F statistic is different from the T statistic before. So this is the F statistic, and the T statistic was a different number. But if you look at the p-value and the p-value in the original table, that would actually be the same. So if I'm to scroll back up and notice the original model, you see how the p-value is exactly the same on the coefficient on experience. So the t-value is different. This is the test statistic because it's a different test. This is a t-test versus an f-test, but the p-value is exactly the same. So this tells you that both tests, a t-test and an f-test, would produce exactly the same results. Okay, so what we learned here about how to do a t-test, we are going to be repeating it 3 more times, and we're going to make it more and more complicated each time, because now we're going to be testing for joint significance of several coefficients here. Okay, so we will now test for several coefficients to be jointly significantly different from 0. And this is actually typically what the NEF test is used for. So in this case, let's test whether the beta coefficient on experience and on tenure are significantly different from 0. So again, the unrestricted model would be the same as we had before. So this is the same as model unrestricted. But the restricted model here, notice how it doesn't have experience and tenure in here, because these two are not in there, because we restricted those coefficients, beta 2 and beta 3, to be equal to 0. So now we're estimating a new restricted model with 2 restrictions this time, where wage is only regressed on education and female. So again, we don't include experience or tenure here. And summarizing this model. So here is the results that we have from this model. And we want to pick up the sum of square residuals from this model. So again, from the model that we have above here, we're going to be picking up the residuals, squaring them and summing them up. This is going to be the sum of squared residuals for this restricted model. Same for the unrestricted model. We have that information from above. So here we have the sum squared for the residual for the unrestricted model. Here's for the degrees of freedom for the unrestricted model, and Q equals 2, because now we're testing for 2 restrictions. Well, the first one is that the coefficient on experience equals 0, and the second one is that the coefficient on tenure equals to 0. They're tested jointly. So the same way to form the F statistic, here we are doing the sum of square residuals for the restricted model minus the sum square for the unrestricted model divided by Q, and then divided by the sum square for the unrestricted model divided by the degrees of freedom for the unrestricted model. So this would be the here the F statistic that we have here, and the F critical value and the p-value would be denoted here. So everything is the same as before. The only thing that would be different from what we did before is the degrees of freedom for the numerator here would be changing to Q, which is now a 2. And the rest would be the same. So since we calculated these the F statistic, we can compare the F statistic to the F critical value here. And notice that the F critical value changed a little bit because the degrees of freedom Q is now 2. It's not 1 as we had above, but it's still a number similar to what we had before. So here we have the F statistic greater than the F critical value. Therefore, we conclude that these coefficients are jointly significantly different from 0. And if we look at the p-value for the f-test, the p-value is less than 0.05. Therefore, we reject the now, and the coefficients are jointly significant. The way to do it much faster, just using an R command, because no one would do it like slowly like that when we have this line here. We would be doing linear hypothesis. Here we would be giving the unrestricted model. So the unrestricted model is this model here that has all of the variables in the model. And then we're going to be testing here for the coefficient on experience equals 0, joint test with the coefficient on tenure equals 0. So notice that again, this is that not that the experience itself is equal to 0, but the coefficient on experience and tenure are equal to 0. And this is the p-value that we have here. This is the test statistic for the F distribution that we calculated above. And we're concluding again that the two coefficients are jointly significant. So this is much faster way to do what we did with many lines up here. Okay, so I will repeat the same thing a third time. So this time we're doing exactly the same thing, but we are going to test for overall significance, where we are testing for all coefficients to be jointly significantly different from 0. So because we want to test basically if the regression makes sense, if all of the variables are jointly significantly explaining the dependent variable. So here the null hypothesis would be that the coefficients in all of these are not significantly different from 0. The alternative would be that they are jointly significantly different from 0. We are calculating the restricted model, which is wage regressed on a constant. So for that, if we just regress wage on a constant, one thing that we're going to be finding is that the coefficient here is exactly the same as the mean for the wage variable. So I went ahead and showed you the results here for running a linear model of wage regressed on only a constant, because we have restricted all the other coefficients to be equal to 0 from the wage 1 dataset. And this is the only coefficient is on the intercept, so this is 5.89. And so here we can use the stargazer to be looking at the data set and for the wage variable and summarize it. So here, if we summarize the wage variable, this is the same mean as this intercept. So that's actually what's happening. when we miss all of the independent variables from this model. Okay, so now we can again estimate the unrestricted model, and then we can basically check here the F statistic from that model. So here we actually the F statistic is reported in the output right here, and then we have the degrees of freedom here 4 and 521. So this 4 is the number of regressors, so 1, 2, 3, 4 regressors, and here this is n minus k minus 1, so 526 observations minus 4 variables minus 1, and this is the p-value. So this F statistic for an overall significance is already reported as part of the output. And so here we're concluding that because the p-value is less than 0.05, we have actually overall significance. So this means that these coefficients are jointly significantly different from 0. So if we look at them individually, this is significant, this is significant, this is significant, but they're also jointly significantly different from 0. And we can actually call a summary from the model here and then call the F statistic element. And this is basically the F statistic here as well. Okay, so to just recap very quickly, we can actually do it the slow way, which is estimate the unrestricted model. Now we have Q equals 4 degrees of freedom. Calculate the F statistic just like what we did above, and then we can also calculate the F statistic in an alternative way using the R squared. So the F statistic is also equivalent. This formula that we see up here is also equivalent to this formula down here. And so basically, if we pick up the R square here, and k, the number of independent variables, we can actually calculate the same F statistic here as well. So let's see, if we calculate the F statistic both different ways, here we see it using the regular formula that we had above, and this is the other formula using the R squared, so we would be getting exactly the same results here. Then using the F critical value and calculating that, and also the p-value for the F test as we did above, this is the F critical value. We would be comparing the F statistic to the F critical value. So because the F statistic that we calculated here is greater than the critical value, we have the coefficients are jointly significant, and the p-value is less than 0.05. Therefore, again, coefficients are jointly significant. If we want to use the R commands, we would be using, again, linear hypothesis using the unrestricted model. And here we would be testing if all of the coefficients are jointly significant. And what we have here is the results for the output, which is we are basically seeing the same F statistic that we saw before displayed in the output, and this is the p-value for it. So therefore, we have that the coefficients are jointly significantly different from 0. Okay, so this notice that again, the F statistic here and the F p-values are the same as reported in the regression output. The last thing that we're going to do here is talk about the Lagrange multiplier for coefficient significance. So this is not as commonly used as the F test, but we can use it. So this is a chi-square test for several coefficients to be jointly significantly different from 0. So again, this is the unrestricted model here. And if we want to test again that these two coefficients are significant, we would be estimating the restricted model here. So notice that tenure and experience are not included here. So we are going to be regressing the dependent variable on the restricted set of the independent variables. This will be the same as the second restricted model that we estimated from above. And here we would be having 2 as the number of restrictions because, again, we're testing for 2 coefficients. So the way to do this in the Lagrange multiplier test is to get the residuals here from the restricted model. And we would be using uh, residuals from the restricted model. We would be calling this wage 1 E hat. So basically, we would be that's how we would call these residuals. And here we would be regressing the individual's E hat on all of the independent variables. So here E hat is regressed on all of the 4 independent variables that we have here. We would call this model E hat. So now notice that we don't have wage regressed on all the independent variables. It's the residuals from the restricted model that are regressed on all the independent variables. And in order to calculate the LM, the Lagrange multiplier statistic, we need to multiply n, the number of observations, times the r squared from the above regression here that we have. And here is n, we're picking up n for the number of observations. And then r squared, it's from the model for E hat. So basically we're going back into the restricted model. We are picking up the R squared. And here we're basically calculating the N times R squared. And this will be the LM statistic. So this is the Lagrange multiplier statistic that is distributed as chi-square. So the critical value for a chi-square distribution, we're going to be using Q for chi-square distribution. P is equal to 0.95. This degrees of freedom are equal to Q. And the p-value, we're going to be using P for chi-square. We're going to be giving it the test statistic, and then these would be the degrees of freedom, and lower tail would be false because it's a upper one-tail test. And looking at the critical value, because the test statistic is higher than the critical value, we would be rejecting the null, so coefficients are jointly significant, and the p-value is less than 0.05. Therefore, the coefficients are again jointly significant. So what we learned today is how to do hypothesis testing in linear regression.